Hey guys, welcome to a new video on trigonometry with me, Angad. Today our video is all about doing a recap of my last two videos. My last two videos were on trigonometric questions and answers and complementary angle relations for trigonometry. This is part 2 of my trigonometry basics recap. My part 1 was on Sawakatawa using Pythagoras theorem to find unknown sides and angles and trigonometric ratios for specific angles. So let's start with questions and answers as we always do. Here are 5 questions. Question number 1 is a diagram based question. The diagram is where my mouse is pointing. It's on the left hand side corner. So you can pause the video for 5 to 10 seconds or minutes and then work out your answers and then play the video. Here is question number 6 to 9. So these questions are of my complementary angle relations. So you can pause the video for 5 to 10 minutes or seconds and work out your answers and then play the video. This is last but not least question number 10. Question number 10 is a bit of mix and match. It's about testing your knowledge of trigonometric ratios for specific angles, the roots, under roots, quad roots, cube roots, etc. and the complementary angle relations, of course. You can pause the video for 5 to 10 seconds and then play the video. Here is the answer to question number 1. In this slide, the question number 1, the working out which I have given you, it's very easy and very transparent. So you can see the answers on your own and you will understand them very easily. But on the next slide, which is question number 1 in continuation, I will be explaining a bit of it. You can pause the video for 5 to 10 seconds, work out your answers and then play the video. So let's discuss this slide. So in this slide, in the previous slide actually, I have found the values of sine dBA, which is 1, which is actually 15 by 15, but that is 1. You get the gist, don't you? So cot BDA is 12 by 9, which is equal to 4 by 3, a simplified form. And cot BDC is 12 by 5. 12 by 5 can't be simplified, so we just write it as 12 by 5. And in the equation, they have also asked, not the equation, the original question, they have asked us to find the value of the cube the cube root of 729. So the cube root of 729 is 9. So now that we have got the values of all these 4 necessities, we will now substitute the values of these functions and the cube root of 729 in the equation. After substitution, it just becomes an easy fraction and which will be easy to solve. And the answer is 16 by 45. Question number 2. In question number 2, I think this is the most easiest question, because in this question all of the sides have the same variable. So you just have to use the Pythagoras theorem. Just a thing which is important. You cannot use the parameter rule, that is to just add the measurement of the sides, because you can use the parameter rule only and only if you have the measurement of the parameter. If you don't have the measurement of the parameter, well, then you can't use the parameter rule, which is to add the measurement of all the sides. But in this case, you can use the Pythagoras theorem because all the variables are the same. In step number 4 and 5 and 6, in this 4x squared is equal to 20x. You can just, if you're smart enough to understand, you can just cross out the 2 and the x. But if you're not smart enough to understand, no offense, but you have to expand the 4x squared, which is 4 into x is equal to 20 into x. Okay? And then you can either transpose 1x to this side or 1x to this side, because it would make no difference. If you transpose the x from the LHS to the RHS, it becomes 20 into x divided by x. And x divided by x, we're following the BODMAS by the way, x divided by x is 1. So 20 into 1 is just 20. And then this becomes 4x into 20 is equal to 20. And then x is equal to 20 by 4 and x is equal to 5. Now you can substitute the value of the x in the actual numeric or the numeric and alphabetical equational measurement of the sides, and then find the exact numeric values. Here is question number 3. Question number 3 is, I think it's from my second video. No, yes, it's from my third video. And this one was just about substitution and your precise understanding of quad roots and cube roots and etc. etc. So in this question, the base is the quad root. That sounds pretty cool, eh? The quad root of 256, which is equal to 4, and the parameter is the quad root of 65,536, which is 16. So now that you have the values of the base and parameter, what you do is that you use the parameter rule, which is the addition of all sides is equal to the parameter. So in this, I have chosen my altitude to be xz and hypotenuse to be yz. If you have any different values, because in this one they have just given the value of the x, but it's okay. If you have a different value, it doesn't matter, but as long as you have the same answer, it's fine. But in exams, if they have written that the base is xy and the right angled x, then it should be xz and yz. So now xz plus yz plus xz is equal to 16. So xz plus yz plus 4. The reason why there is a 4 is because the value of xy, which is the base, by the way, is 4. So xz plus yz plus 4 is equal to 16. Then you transpose 4 to the other side and it becomes 16 minus 4, which is 12. Now xz plus yz is equal to 12. Now by transposing yz to the RHS or the xz to the RHS, you can find the value of xz and yz. Now using the Pythagoras theorem. Just a note, in questions like these, you do not, and you do not, trust me, don't write h squared is equal to a squared plus b squared. You have to write yz squared is equal to xz squared plus xy squared, because you have the value of yz or xz. Okay, that's why we write yz squared, xz squared, and xy squared. If you had written hy squared, h squared, a squared and b squared, you have to mention, like I have mentioned it here, that the base is equal to this, the parameter is equal to this, the altitude is xz, and the hypotenuse is yz. Because if you don't, the examiner or the person who is marking your sheet would say, "What's this? I don't know what it is." So yeah. So if you write like this, it's okay, and if you don't, you write h squared, and then in the second step you write this form. You have to mention that the altitude, hypotenuse, and the base is this. But to be on the safe side, you can write the base, altitude, and hypotenuse in the exam. So now after substituting the value of the hypotenuse and the base, we get 12 minus xz squared is equal to xz squared plus 4 squared. Just a note, you can substitute the value of xz also. What I mean by that is you just have to substitute only one value, but it can be yz or xz. It doesn't make a difference. But you can't substitute both of them, because then it will come in this same equation. So 12 minus xz whole squared is equal to xz squared plus 4 squared. Then using the a minus b whole squared formula, 144 minus 24xz plus xz squared is equal to xz squared plus 16. On transposing either of the xz to the LHS or the RHS, they cancel out. So it becomes 144 minus 24xz is equal to 16. Then I transpose minus 24xz to the RHS and 16 to the LHS, because I'm putting the like terms in on one side of the equal sign and unlike terms on the one other side of the equal sign. So it becomes 24xz is equal to 144 minus 16, which then becomes 24xz is equal to 128. Then xz is equal to 128 by 24, and then on simplification it becomes 16 by 3. Therefore the value of the altitude is 16 by 3. Now that you have the value of the altitude, the the base, you can use the Pythagoras theorem to find the value of the hypotenuse. So the value of the hypotenuse is 20/3. Now you find the value of cot y, cot z, sin y, and sin z. Question number 4. This question is from my third video. If you watch it carefully, this was, I think, on the challenge questions. So 20 sin x minus 5 cos x in brackets is equal to 6 cos x. So 20 into sin x minus 20 into 5 cos x, which is minus 100 cos x. So 20 sin x minus 100 cos x is equal to 6 cos x. Then transpose 6 cos x to the LHS, and then it becomes 20 sin x minus 100 cos x minus 6 cos x, which is equal to 20 sin x minus 106 cos x. Then 20 sin x is equal to 106 cos x. I transposed 106 cos x to the RHS. Then sin x is equal to 106 cos x by 20, and then 20 is equal to 106 cos x by sin x. I could have just written 20 is equal to this in the third step, but I chose not to. It was a longer step, and I thought it would explain you guys it a bit better. So then 106 cos x by sin x can be written as 106 multiplied by cos x by sin x. Then transposing 106 to the other side, 20 by 106 is equal to cos x by sin x. Now if you guys remember the fact that tan is equal to sin by cos and cot is equal to cos by sin, then 20 by 106 is equal to cot x. And then 10 by 53 is also equal to cot x. And then, as you know, that cot is the reciprocal of tan. It becomes 53 by 10 or 5.3. Therefore, the value of tan x is 53 by 10 or 5.3. Question number 5. Question number 5 is just like question number 4, so I will not be explaining this question. But in this, I've written a statement on properly transposing. You can't write this in the exam because the examiner might decrease your marks or cut your marks. So you have to give the exact working out like I gave it to you here. So you can pause the video for 5 to 10 seconds and then check the answer and you're working out, and then play the video. Question number 6 and 7. I will not be saying question number 6 because it's just the complementary angle relations. Question number 7. Is sin p plus q is equal to 1 by root 2? Prove or show that tan p minus q is equal to cot 45 plus 2q. So, as per my memory, I remember that sin 45 is also equal to 1 by root 2. So sin p plus q is equal to 1 by root 2 is equal to sin 45. So then it becomes sin p plus q is equal to sin 45. Using the fact that sin a is equal to sin b, a is equal to b, p plus q is equal to 45, p is equal to 45 minus q, and q is equal to 45 minus p. Now we will substitute the value of p in the relation, in the LHS of the relation. It becomes tan 45 minus q is equal to cot 45 plus 2q. Then it becomes tan 45 minus 2q, because minus q is 2q minus 2q. Tan 45 minus 2q is equal to cot 90 minus 45 plus 2q. I have used the complementary angle relation in the LHS of the equation, of the relation, no pun intended. It becomes, then using the complementary angle relation, it becomes cot 45 plus 2q. Therefore, it is proven that tan p minus q is equal to cot 45 plus 2q. Question number 8 and question number 9. Question number 8 is almost like question number 7, but I will be repeating this question. So using the complementary angle relations on the LHS of the equation, cos b is equal to sin 90 minus b, and I did not use the complementary angle relation on the LHS. I used it on the RHS, by the way. It's just I wrote it wrong, sorry. So now substituting the value of cos b in the equation becomes sin a is equal to sin 90 minus b. Now using the fact that sin a is equal to sin b, a is equal to b, a is equal to 90 minus b, and transposing b to the LHS, it becomes a plus b is equal to 90 degrees. Therefore, the value of a plus b is 90 degrees. Question number 9. So question number 9 is just like question number 8, but just in this you have to use the complementary angle on the other side, and then you have to solve it like a linear equation. But I will not be dictating this question because it's just like that. You can pause the video for 5 to 10 seconds to cross check your answers. And last but not least, but my favorite, question number 10. So, sine squared 56 plus under root 3 multiplied by tan 60 plus under root 2 multiplied by sine 45 divided by cos or just by cos squared 34 plus under root 3 multiplied by tan 60 plus the quad root of 65,536 plus under root 2 multiplied by sine 45. Okay, so now in this equation, if you look at this just like this, you can't just cancel this out, or you can, but you have to give a valid explanation. So let's solve this equation. So now we will use the complementary angle relation in sine squared 56. So sine squared 56 becomes cos squared 90 minus 56, sorry, and then becomes cos squared 34 degrees. Now, so we will substitute the value of sine squared 56 in the equation. It becomes cos 30 squared 34 plus under root 3 tan 60 plus under root 2 sine 45 by cos squared 34 plus under root 3 tan 60 plus 4 by 60, the quad root, sorry, the quad root of 65,536 plus under root 2 sine 45. The cos squared 34s get cancelled out because they are just like each other, they're like terms. And then the value of the under root 3 multiplied by tan 60 plus under root 2 multiplied by sine 45 is equal to under root 3 into under root 3, because tan 60 is under root 3. So under root 3 by under root 3 multiplied by under root 2 multiplied by 1 by under root 2, because the value of sine 45 is 1 by under root 2. So under root 3 plus under root 3 multiplied by under root 3 is 3, and under root 2 multiplied by 1 by under root 2 is equal to 3 plus 1. And now it becomes and the denominator is under root 3 into under root 3, because tan 60 is under root 3, plus the quad root of 65,536 plus under root 2 into under root 1 by under root 2, because 1 by under root 2 is the value of sine 45. So it becomes 3 plus 1 by 3 plus quad root of 65,536 plus 1. The quad root of 65,536 is 16. Now we will substitute the value of the quad root of 65,536 in the equation. It becomes 3 plus 1 by 3 plus 16 plus 1, which becomes 4 by 20, and then becomes 1 by 5. Therefore, sine squared 56 plus under root 3 tan 60 plus under root 2 sine 45 by cos squared 34 plus under root 3 tan 60 plus the quad root of 65,536 plus under root 2 by sine 45 is equal to 1 by 5. So that's all, guys, for today. Please stay tuned. If you like the video, give it a like, share, and please subscribe the video. I'll see you guys in the next video. This was my last video for trigonometry. So see ya. Have a nice day, guys. See ya.